All right, so now we are discussing on RNN, that is recurrent neural networks. So let us start the understanding part of what exactly is RNN. So recurrent neural network. So it is a type of neural network only, and there's some special features which we need to discuss and understand. That why do we call it as recurrent? So that is something we need to understand. Okay. So now the important thing or important feature in a recurrent neural network is the word recurrent itself, which basically means that output from the previous step fed as an input to the step. So that is basically is the meaning of recurrent. The output from the previous step, they are fed as an input to the current step. And so what happens in case of the neural networks which we have been discussing? Now we can call them as traditional neural networks. So in case of traditional neural networks, what happens? We know that the yes. So what happens? So this is input. Okay, so consider this as input. And similar way, we have output here. So yeah, so input is there, output is there, and in between input output, your nodes are there. So I'm just creating one node. So what is going to happen here? The input will be passed through this particular cell, and similar way, it is going to give some output. This is what happens. Okay. If I expand this, then basically expand in the sense if I add some more number of layers. So now you can see I have added more layers. So now this is going to give input to this layer. Similar way from second one, the okay input will go to the third one. From here also the input is going to go here, and finally the node is going to give some output. This is how it is going to happen. Okay. So this is the case with the traditional neural networks. All the inputs and outputs, they are independent of each other. Okay, you can see they have no dependency. And everywhere we are getting the input and output. You can see here also we are getting. Let me create one. Input. And the output of first one is going as input to the second one, right? So this way. And then we have final output only. Okay. So you can see that the inputs and outputs, they have no relation. They are independent. But let's say I have a case, and the case I have is there is a sentence. The sentence is let's say WELCOME, welcome, BACK, back. This is the example sentence, welcome back. Okay. Now, when I was writing welcome, then is it possible to predict that next thing I'm going to write is back? Is it possible? And have you seen such things happening? The answer is yes, it is possible. And we have seen also such things are happening. Okay. So if I will start typing something, I will get suggestions for what next would be coming. I'll be getting suggestions. I'll give you examples. So whenever we are writing some of the, let's say, let me make it 12. So whenever we are writing DAR, dear. So here name is the suggestion. So write dear in case of any email, the name comes as automatic suggestion. Then whenever we write end of the day, this becomes suggestion. Of the day, suggestion. Before we actually write it. Similar way, if I write please find the attached, then files. So please find the attached files here with that would be the prediction. Okay. And you must have seen anything you start writing, especially on LinkedIn, on Gmail, you get such outputs when you write partial sentence. You must have observed this thing, right? That is a part of recurrent neural network. Okay, that is a kind of prediction a recurrent neural network gives. Okay, so this is an application also of RNN. This is an application of recurrent neural network as well. There is an important feature or an important concept, and that is called as, so in case of this type of neural networks, we have something which is called as hidden state, and that is basically like a memory. Okay, it stores some information, or rather storing, you can say it remembers some information. Okay, that is an important concept. So there's a hidden state and it remembers, it memorizes certain thing. So the kind of architecture we have for RNN is, so it is like that, a simple architecture. Let me take some components from here only. We have input which is perfect. Okay. Then we have a hidden layer. Layer is there. And after hidden layer, we get the output. That is also fine. This is how it happens. So we have input layer, we have a hidden layer, and then we get the output. Okay, it happens this way. Now, this hidden layer is only that layer which memorizes. So here you can see that we have, yes, there was a glitch in the network. I hope I'm audible. So I was explaining that. So there is a memory and it remembers all the information. So remembers all the, in simple we can say past information, or rather here I can in. Now is it clear?
Yes, sir. Yes, sir.
Okay, fine. So in case of a neural network, we have so many calculations. So the memory will remember all those calculations actually. So what memory does here is it remembers all the calculations which are done in the past. Okay, now let me take this particular slide and take help of this particular slide just to explain recurrent. So now in case of recurrent neural network, what will happen? So we have input and this one is input layer, and then we have this one, this two, these are hidden layers. Okay, so Let me have them a little closer this side. Okay, and this also, let me take it here. Yeah, and let me take this one here. Okay, one more layer and one output. Okay, the final output. So if required, we can shrink the size of output if needed. And same we can do with input as well. Okay, so here you can see, and let me just remove these parts. So input layer, and this one is the output layer, right? So, and then we have hidden layers. Only two I have drawn here. Maybe I can add one more hidden layer. Okay, so we have good space over here. So let me add one more. Okay, so this one is one more hidden layer. Okay, so these are the hidden layers which we have. Okay, these are the hidden layers which we have. So I can name it as hidden layer 1, and this would be hidden layer 2, and this is hidden layer 3. Okay, yeah. So this we can call it as this is a deeper network. Okay, that's why we call it as deep, because it has got multiple layers. So one input layer, and then we have three hidden layers, and then one output layer. This is how we have, and it has got its own set of weights and biases, the way every neural network is having. And now what they will do is now there at this diagrammatic view, if you see, they are all independent. Nothing is happening like recurrent nature, nothing of that kind is happening. So here, let's say we have um, the respective weights and biases. Okay, let me put them into brackets. So we have respective weights and biases over here, okay, which are associated. And they are not memorizing anything. So if they are not memorizing anything, then what is happening? Then, okay, it will become a regular network. But because we are talking about RNN, recurrent neural network, so here the independent nature of all the layers will now be converted into dependent nature. Okay, so let me add a line over here. Okay, what a recurrent neural network would do. So the recurrent neural network RNN will, so RNN converts the independent activations into dependent, so into dependent activations. That is the task of recurrent neural network. Okay, now how it will do it. One thing can be done here is, okay, like how this can be done. So it can be done by providing same weights and biases. So to all the layers, if you are providing same weights and biases. So earlier, how it would be? So here, let me do write TRADITM traditional. So this would be W1, B1. Okay. So some weight, some bias. To another layer, it will become W2 and B layer. Now you are clear what is happening. This is how it is going to happen. Okay, this way, right? So here if you see that all the weights and biases are getting changed, but if I basically do the same thing as provide same weights and biases to the layers, so that means I can pass the same weights and biases Okay, to this one, to this one, this one. Okay, same weights and biases we can pass. This is how we can do. Okay, so that is what is an attempt which RNN basically makes. First of all, it converts all the independent activations to dependent, and this is a way of doing it that they depend on the same weights and biases. Okay, and now one more thing we will do. So another thing we will do is memorize. Memorize the outputs. So memorizing the outputs. Okay, and so memorizing the output is another thing which is required. So memorize the output and giving this output to the next layer, or rather you can say next hidden layer. So giving this output to the next hidden layer. Okay, so this is what is happening in case of recurrent neural network, memorizing the output and passing it to the next hidden layer. So in our case, what is happening? If this is happening, then we may have the representation of this recurrent neural network, which you are able to see in the with the help of a diagram. So we can have the representation something like this. Instead of having three hidden layers, we can only have one hidden layer. This is perfect. But what we will have is, so what I'm doing here is, you can see, I'm doing this. Okay, this arrow basically tells that it is a recurrent layer. So hidden layer, and let me write recurrent. So you can understand the recurrent nature. This is the recurrent layer. So input layer is there, output layer is there, and in between we have a recurrent layer. Okay. Okay, it will be like this. Yeah, somebody got unmuted. So, right. Now, in order to basically get to know that to compute the current state, we have a formula, and the formula is, we represent the current state as ht, and then we write ht is equal to function of ht minus 1 comma xt. Okay, so you can see that here this is the representation of the formula here ht. So here this ht is the current state, then we have ht minus 1, and this is the previous state, and then we have xt. So xt is the input state. Okay, this is the meaning. And now let me give you one example of it. Now if you want to apply this, then how can you apply this? Now this part. Okay. So this part can be written as, so now what we will do, we will apply, instead of f of x, we will write a function over there. Okay. So f of x is generic form. So we can have a tan function. Okay. So tan h we can apply. So current state is equal to tan h of, and we know we need to have weights. So we will have weight. Okay. So weights we will have, and so I can write it as maybe HH. So let me, yeah. So weight into HT minus 1, then I can have plus weight of here XH to XT. Okay. And here the differences we have are here WHH. So this weight basically means weight at recurrent neuron. So weight is going to remain same. Therefore, WHH is weight at recurrent neuron, and WXH. XH. This is this is how the formula gets completed. And if you want to get the output, okay, then for getting the so so this you can say ACTIVA activation. So we applied activation function, and then you want the prediction, the output. Okay, so for prediction, so for making prediction or basically coming out with Y. So in that case, it will be, so here it will become Y. So Y is equal to, okay, so here YT is equal to WHY into HT. So here WHY is equal to weight at, the weight at output layer, the final weight, and rest we can remove, and just YT. So YT is equal to the final output. So this is how the formula comes in. Fine. So this gives us an idea that how recurrent neural network works. Okay. So we have the input layer, then we have output layer, then we have hidden layers, and neural network gives them same weights and biases. So we can have iteration, or multiple times the hidden layer can execute and re-execute and re-execute. Okay. Current state, activation function, and making prediction of the output that I have shown you. Now the flow, okay, how the training will happen in this particular case, let me show you that also. Okay, so here the first thing we would require is we will give input, and the input would be single time step. We'll be giving an input, and this will be single time step. Okay, second thing, so we would like to calculate the current state. So first is a single time step would be input. We would like to calculate the current state with the help of using the current input. Okay, we have the current input and the previous state. So we'll calculate the current state. Now this current state becomes the ht minus 1. So you can see that as soon as your current state is out, then it becomes the previous state, right? So it becomes ht minus 1 for the next you can say time step rather. It is going to become the ht minus 1. Now you can go for n number of time steps. Okay, n number of time steps. Now once all the time steps are done, then what you can do is, okay, so final current state, that would basically produce the output. So this is how the training will happen. Now we know we need to optimize. Okay, and for that we have back propagation. So we will have loss or error or error. So okay, so that will happen with the help of back propagation. Okay, fine. Now just to summarize and conclude this, so we may have some advantages or benefits, and okay, similar way we will have some disadvantages also. So the advantage itself, the first advantage itself is that it remembers. Okay, it remembers each and every information. That is the first advantage. And this advantage itself leads to time series analysis, helps in time series analysis, which we will see. Okay, that is also a part which is called as LSTM, long short term memory. Okay, and they are also used in CNN. That is another benefit. The purpose is to increase effective. So, so there is a benefit, and wherever we have benefit, then some sort of challenges or problems are also there, right? So to any concept, if there is a benefit, then we have some challenges also. Now, what can be these challenges or limitations? Limitation, there is one problem which is called as gradient vanishing problem, and second problem is gradient exploding problem. Okay, training is difficult, yes. Processing very long sequence or input, okay, is again a challenge. So I think these are good enough. Okay, so these are the challenges. Okay, these are the challenges which it faces. Now let me just tell you about two things, which is one is gradient vanishing problem and gradient exploding problems, because they are quite important, and uh, they are being discussed. Okay, so vanishing. So vanishing, you understand what happens? That that is coming to nothing or coming to zero, something which is coming to zero. And here we are talking about gradient. Okay, so if we have multiple iterations or multiple time steps, there is a possibility that the derivative, it decreases, and the value is becoming either zero or very close to zero. Okay, and if the value is coming to zero or close to zero, that is called as gradient vanishing. Okay, this basically means that the value of the product derivative. Actually, there is a chain rule which is applied. So the value of the product derivative decreases. Okay, that is one thing. So it decreases. And that is not the problem. Decreasing is not the problem. But it decreases to such an extent that it becomes close to zero. This is the problem. It becomes close to zero. Okay. So the value of the product or the derivative decreases and it becomes close to zero. Okay, that is what happens. That's the problem. So vanishing means the value becoming close to zero, or I can write it as partial derivative. So I can write it as the partial derivative actually vanishes. Okay, therefore the word vanishes is written. So this is a problem. Then now further you can't compute, right? You cannot compute now. Now exploding is opposite of it. Here what happens? The derivatives, they get larger and larger. So same thing but opposite will happen. And what is happening here? The value of the product derivative increase. Okay. So when it is increasing, yeah, so it increases, and when it is increasing, it becomes larger and larger. So this itself is a problem. Okay, so it is an opposite. Okay, this is an opposite to vanishing gradients, and the primary reason for this is, like, why this happens is it happens because of the weights. Okay, so weights are responsible for it. Okay, so these problems also we need to tackle. Okay, so we need to find some solution to vanishing, like we need to change some activation functions, or we need to look into the hmm. So we need to look into the weights, that how the weight should get optimized. Okay, that is something we need to do. Okay, fine. So this is an idea of RNN, that how basically RNN, what RNN is, how RNN works, how it looks like diagrammatically, and then how the training happens, what benefits do we have, and what limitations we may have. Now let us go back and let's have a new file created, and let me create a new notebook. So in this particular new notebook, let's work on RNN. Yeah, so everyone can get the new notebook created and we'll work on it. Okay, so this is RNN implementation. Put the libraries, and we will have import as NP. We will have TensorFlow, import TENSOR tensor FLOW flow as TF. Then we will have Keras as well. So import KERAS Keras. We'll have to import import TNSOR TensorFlow dot KERAS Keras. That is how. And then we will have to get layers also. Let's import the layers as well. So from TensorFlow.keras import layers. I think these many are good to start with. Okay, fine. So let us create the model. So model is equal to, we will have keras dot. So yeah, and we will have layers here. So first we will create model. We did not import the model. So keras dot sequential should do. So model is equal to keras dot sequential, and this is going to create the model. And let me just do it this way. Let me simply make it from TNSOR TensorFlow dot keras import keras dot model model import sequentil sequential. And here let me just use what happened. Yeah, so it should be models, and here let me just directly use sequential. Okay, so model is equal to sequential. We have created sequential model. Now let's move ahead. Model.add add, and here we need to add the layers. So from layers, so layers, we will have yeah, so layers dot embe, yeah, embedding, and into this we will have input dimension. Input dimensions here, we will take input dimensions as 1000, and output as 64. Fine. So one layer we have added. We need to add one more layer. So model dot add. Okay, it is like yesterday only the way we were doing. So here model dot add, and here I'll be adding layers dot LSTM. Okay, because we are talking about recurrent neural networks, and the size I'm passing as 128, number of units I'm passing. Then I'll connect it to a fully connected layer. So model dot again add layers and dot dense. This is very common. So with dense, I'll just have 10 units. Okay. So I have added one dense layer. And now I can just do model.summary summary. Here you can see this is my model I have created. So you can read, okay. I have an embedded layer, I have LSTM, I have dense layer. Okay. So this is how my model has got created. Okay. A simple way of creating a model. And we are not compiling or doing anything, we just created the model. Okay, so you can just create it. So here's the code, a simple model. Okay, before we move ahead to an example of it. Yeah, so let me plan a data set on which we will work. Yeah, so what we will do is, let me create another notebook for another example. So this implementation will be quite lengthy. So just give me a minute. I'm trying to help you with a simple implementation first. And then in the second case, LSTM, we can go for a lengthy one. Okay. So let us use that MNIST dataset only. Okay, the MNIST dataset which we had used for handwritten labels. For that only, let us use and work on it. Okay, so there basically we will apply RNN. Okay, so this program we'll create for RNN for MNIST and WRITT handwritten dataset. Okay, so yeah, let's work on this. Again, we need to import certain libraries. So import the libraries, and let me start with TensorFlow, and then I'll have to go with Keras and the layers as well. So import TensorFlow as TF. Let me enlarge it a bit. So import TensorFlow as TF, and then from TNSOR tensor FLOW TensorFlow.keras keras dot models import we need sequential, and then from TensorFlow.keras dot layers import we need dense layer. Okay, we need dropout. We discussed day before yesterday that dropout is used for preventing the model from the overfitting part, and LSTM. So these libraries we do require. Okay, fine. So let's have the data set loaded. Load the data set, and for that mnist is equal to, we'll have tf.keras dot datasets dot mnist, and Yeah. And here x underscore train train comma y underscore train, then x underscore test comma y underscore test is equal to mnest dot load underscore data this way, and it will get loaded. So yeah, so it's getting loaded. Then we do normalize the data. So normalize normalize. Okay. So x underscore train is equal to x underscore train divided by 255. Similar way, x underscore test is equal to x underscore test divided by 255. So we are normalizing the data, and let us just see the shape of x. So x underscore train dot shape, and and then we will see the shape of x underscore only train of 0. Okay, we'll see the shape of this shape. Okay, so you can see that for one particular item, the shape is 28 by 28, that we know, and 60,000 is the total number of data items we have. I think day before yesterday, this particular environment was facing difficulty to process so many records. So we'll see. Okay, let's move ahead, and let's work on it. Hmm. So here, if you remember that, what is our input here? The input is your MNIST hand written data. Okay, and what do we actually do is we flatten the data. Okay, I hope you remember flatten also. So normally we flatten the data. And what happens by flattening? By flattening, the data which is present into 2D array, it becomes 1D. It becomes one dimensional. Okay. So ultimately it is data only, right? So images, once it is represented in the form of arrays, so it's data. And we had discussed one more thing, that this data, okay, the property of this data is like you reshape that data, but it doesn't in CNN we had seen. Okay, so if you reshape or if you transform or transpose this particular data, then basically it doesn't actually make much sense. Like the much change, the sense remains same. Okay, so I was telling you that one object may stand, one object may sit, one object may lie down. So in all the cases, what happens? In all the cases, it shouldn't happen that you know that if some object is sitting, then it means different thing. So the data is basically whatever maybe the shape of the data, reshaping the data should not actually change the properties, the primary properties or features of the data. Okay, fine. Create the model now. For creating the model, model is equal to sequential and add layers. Okay, del model dot add, and add the layers over here. So LSTM is one of the layers we need to add. 128 nodes would be there, and input shape, input underscore shape would be, so input shape would be x underscore train dot shape shape, and that too what we will do is, yeah, so x underscore shape, and 1 colon. So for a particular image, if you see 28 by 28 is the shape, so we will use 1 colon here. Now after this we have, now next, so input shape, after that activation function. So let us use ReLU activation function, and then we need to return sequences. Okay, so return underscore sequences, return sequences. We have to make it true. Okay, this is one layer we have added. Now model dot, we'll add dropout layer, dropout, and we just need to mention that uh, how many nodes needs to get dropped out. So I'm just telling 2% of the nodes should get dropped out. So model dot add dropout layer we have added, and then once again I'll add LSTM and then dropout again. Okay, so model dot add, and here I'll add LSTM, and again 128 is the number of nodes which we have, and ACTIVA activation. So activation is equal to, here also it is ReLU. Okay, and this is LSTM layer. Again one dropout layer we will add, model dot add drop dropout. So and dropout percent would be 2%. Okay, so two LSTM with dropouts we have done. Then now let's have a dense with dropout. So model dot add dense, and in this dense layer we will have 32 nodes, and activation function we'll have ReLU only, ReLU, and then let's add model dot add dot add dropout, and again 0.2. Okay, done. Okay, now final output, because 10 digits are there, so final output model dot add, and here dense dense, and we'll have 10 nodes, and we will have activation here as softmax. Fine. This is the final layer. Softmax we use in the final one because it gives the output. Okay. So here the whole of the model which we have made, it is same. The only change which we have done is we have just used return sequences is equal to true. Okay. That is only we have done, nothing else. Okay. Fine. Now let's go for the next thing. Now let's use the optimizer, and the optimizer. So tf.keras dot op optimizers. So here I'm using Adam optimizer. Learning rate I'm keeping as 0.001, very small, and there is a parameter which is called as dk. We need to again keep it very small, so I'm keeping it as 1 raised to like 0.000000, so 3 times 6 times 0, so 1 e raised to 6. Okay, LR use learning rate instead. Okay, no worries, I can use learning rate, learning underscore RET, learning rate, yes. So with time some names get changed. Now compile the model, model.compile, compile, and then here LOSS loss. In this case, sparse categorical loss we will use. So loss is equal to here SPARSE, sparse, categorical cross entropy. So here we have sparse categorical cross entropy we are using, and optimizer we are using OPT, that is Adam optimizer. So optimizer, it's not giving suggestion, fine. Optimizer OPTI ZER is equal to OPT, and then we have metrics equal to accuracy. So accuracy will go for, okay, take this accuracy. Okay, so we have compiled, fine. Now we have our input data sets. So now train the model. So model dot fit fit, and here I have x train, and then I have y train. Okay, then epochs is equal to, so epochs will keep very small, just 3 I'll keep. Okay, I think that should also not become large. And validation data, I'll put the test data for validation. So validation for DATA data, VALI, DATA and validation data is equal to, so I'll pass X test and Y test, Y underscore TST test. So you can see it is getting trained and accuracy is very poor. You can see accuracy is slowly increasing. Okay, 30%, 34%. So let it run. So you can see that when we are using with the help of the Python packages, it is similar, right? So I'm not basically doing something very unique or very different the way we did day before yesterday. Similar steps we have. The only thing is one or the, yeah, can you please mute? Can you please mute for a while? So yeah, so you can see that only very basic changes we are doing, which we are conceptually discussing, and we are just trying to identify that how can we make those basic changes in the parameters. That's what we are doing.
Participants,
Somebody
please
has
mute yourself. Kushal sir, are you able to unmute you?
I thought I was
Yes,
unmuted
yes,
only.
yes,
Okay,
yes,
yeah.
sir.
So yeah, so I was telling that here the only limitation or challenge which we will face is our hardware. Okay, because we have normal machines where we are practicing. So if we will increase the number of epochs, if we are increasing the number of input data records, that is going to slow down, or it will take very huge time in order to process. So therefore, I just kept it 3. Number of epochs I kept it 3, out of which one is completed. You can see the second one is running. It's 1134. You can see that. And the good thing is loss has been really minimized, and accuracy from first epoch to second, we can see that it has increased. So the second is about to over now, and let's have the third one also completed. Okay, meanwhile it is running, I will add this piece of code in the classroom. So this is named as RNN for MNest. So meanwhile, I will just add this in the classroom. So this is RNN for MNIST MNIST and WRITTEN written dataset. So now the third epoch is running, you can see. Okay, so let it complete. After each epoch, we are able to get better accuracy here, and the loss is also getting minimized. You can see that the loss was 0.5757%. Accuracy it was able to achieve was 0.81, that is 81%. Here the loss was minimized to 0.16, and then here if you see the loss was the accuracy was 0.95, and further the loss is minimized 0.1148, and accuracy is also increased to 0.9705. Then we have validation loss and validation accuracy also, because when we pass the training data, along with that we pass validation data also, right? So the test data we had passed as validation data, and you can see that the validation accuracy is also increased. Rather it is more 98%. Okay, it is more than that the training data, you can see. Okay, so this is how we have got the training done. Fine. So this is how we have got the model learned. Okay, it has learned from the X train and Y train. Fine, it has learned from there. All right. So this was RNN for MNIST handwritten dataset example, that how we trained and how we try to optimize, and we got optimized results. Fine. So now let me set some scenario, and then basically we will try to work on that. Okay. Uh, Okay. So let me have one more notebook created. So this time let's think of finance data, and into finance also we have stock market data set, or we have cryptocurrency data set. So we can use the RNN for that also. Okay, so let me create that particular scenario, that what sort of things will we be having. So this small program would be prediction of, okay, let's go for cryptocurrency. Okay, so cryptocurrency financial data set. Okay. Now, although here we will have a new something new to discuss and understand, and that is time series. Okay. So when we do analysis, so we have something called as time series analysis, and very simple and layman's term, if I talk about time series, then time series is data with respect to time. With respect to time, that is called as time series data. Okay. So the data sets which are related to stock market or cryptocurrency, these data sets basically are time series data, because they come with time. They are bounded with time. Okay. So these are time series data. They are related to time. And so what happens in time series data? Let's say we have a time which is t. Okay. We have time t minus 1. We have time t minus n. Right. So you can see that t can be considered as current time, and accordingly now you know everything. T minus 1, okay, 1 time back from current time. So one time step back from current time, that is t minus 1, right? So what happens in any time series data? Like normally, I think on day one I showed you some regression or something. Day one or day two, I had shown you regression part. Okay. So in case of a regression, what happens? In case of a regression, if you see that if we have let's say speed is equal to distance upon time, right? So speed can be y is equal to distance upon time. Okay, so distance, distance, which is x1 upon. So time I'll take it as x2. Okay, this way. Now I can represent this as y is a function of x1 and x2. And the kind of function which is getting created is y is equal to, okay, if I want to get a relationship, okay, then how can I get it? So I can get beta 1 into x1, beta 2 into x2 plus some value which is beta naught and plus some error. This is how also I can represent it. And this is equation of, okay, coming from equation of line for regression we use. Okay, predicting the value of y if some input values are given, and if you have the knowledge of beta 1, beta 2 and beta naught, then you can make prediction of what is y, right? Now if you see that here, the changes in x will lead to changes in y. Changes in the speed will lead to changes in y. Changes in so regression, basically we have one variable and we have another variable. Change in the second variable leads to change in the first variable. That is regression. But in time series, if you will see that there is only one variable. Only one variable is there. So how to observe it? So in case of time series, there is auto regression. There is auto regression. Auto regression. Okay, automatically it will happen. So what will happen? What is auto regression? Auto regression says that we have only one variable only. Let's say price is the variable. Okay, price is the variable. But I am calculating price. Okay, P at time t minus 3, price at time t minus 2, price at time t minus 1, and price at time t. This is what we want. So this becomes very clear, right? Now, what sort of values do we have? Let's say we have a value here as 100, then the value changed and it became 110, then it became 120. So if you see that how the things are happening here, 100, 110, 120, so pt t minus 3, t minus 2, t minus 1 and 130. Okay, that's it. So in this particular case, let me just comment them. Yeah, that's it. In this particular case, you can see that there are no two different variables, rather only one variable is there, but we are looking at the data with respect to time. That is the difference. So auto regression is happening with respect to time, that a variable can tell about itself. So I should reorganize my sentence. So here, past value of a variable in the so past value of a variable can explain the current value of the same variable. This is auto regression. Okay, that happens in case of time series. Okay. Now, the case of stock data or cryptocurrency data we will have. So we will have data features, and the kind of data features we will have, there will be a value called as open, there will be a value called as high, then another value would be low, then another value would be close. Okay, so open will be there, high will be there, low, close, and volume will be there. Okay, so these columns or these features will be there, and data can come from different cryptocurrencies. Two of them would be Bitcoin, Ethereum, THE, REUM, Ethereum. So you can have certain more like Bitcoin can be there, Ethereum can be there, Litecoin is another, so Litecoin could be there. Then any other could. Okay, so whatever popular different. Okay, so what we will do is we will focus on not all the parameters, but we will focus on only one or two to basically look upon the whole to complete the whole analysis. Okay, so let's say we can go for open or we can go for close. So if we go for close, and let's say there's volumes. Okay, so one is close, another is volume. Now close basically, open is the starting price of the stock and close is the final price at the closing time. Okay, measure the what? It measures the final price of the cryptocurrency. Fine, yeah. So measure the final price of cryptocurrency by the end of the day. You can call the day as interval over here because that is the end of the interval, right? And now volume is how much is the how much is the asset was traded. So you can write it as how much is the asset which was traded in an interval. So these two columns we can pick and work upon, the close and this one. Okay. 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 Anything else do we need to consider before we actually analyze? Few more things as a part of pre-processing. So first thing is that balance or imbalance data. Okay. Balance data buy and that is one thing. Okay, balance the data between buy and sell. So the number of records should be similar. Then we need to normalize. Okay, so you have seen that I always I have been normalizing the data, which is basically nothing but scaling the data. So use some method, any method you can use, just to normalize and bring it to a certain limit. Then another thing is create to 30% of so 20 to 30% training data is good. Okay, so you can create 20 to 30% of the training data, which is good enough. Okay, fine. So these are certain things which you can look upon before we actually get into this thing. Okay. Now, another thing is we need to get the data. So I will add the data into classroom. Okay, that is something I'll do. So let me help you with that. Yeah, so in the classroom, if you will go under the dataset section, there you will see this data. Yeah, so go to this particular section, you will get the data here. Data sets, where is the data set? See this one. So under data sets, where it got added? Yeah, let me put it under data sets. So yeah, where is here. So this is cryptocurrency data. Just click on this particular link and it will help you to download the data set. A zip file it will give you. So get that data set downloaded. Okay, so once you have the data set downloaded, then again go back and open that particular file. Yeah, so right click on it and extract. Yeah, extract it. Yeah, this one is the data. So you can get it downloaded. Zip file, extract the zip file, you will get this. Okay. So once you have got this data downloaded, this we need to upload. We'll have to upload it. So if you have downloaded and extracted, then let's just have a look at the data by uploading it. So here is my notebook. And you can use pandas itself to upload it. Okay, in the basic sessions we had discussed on pandas as well. So import pandas pandas as pd. Yeah, and I'll have to upload those files over here. So let me upload crypto data. Now uploading these files and say okay. They're getting loaded, you can see, right? So meanwhile, I can just write data is equal to, so it will create a data frame. So pd dot, they are all CSV files. So read underscore CSV, it will come. And here I need to put the path. Okay, so I think this one is just about to load. Yeah, so all of them have got loaded. So let me just take the path of one. So copy the path and I'm putting the path over here. So I have put the path, and now if I just click on the data, okay, file is too large to display. No worries. So here, open. I just want to see. Okay, that how the data is there inside the files. So you can see this is how the data is there. 1, 2, 3, 4, 5, 6. 6 columns are there. Okay. Starting from here. So the first one is actually related to time. Second is low. Third is high. Fourth is open. Fifth is close. And sixth is volume. Okay. And the data is not having heading, so we will give the heading also. So going back here, so what I will do is I'll give the names also. Here only I'll give the names also. So inside this you can write the names of the, so here you can write names of all the columns. That is something you can do. So let me give the names of the columns. Names, and names would be, first one is time, second one is low, third one is high, fourth one is open. Yeah, so open, and we have close, and then we have volume. And just have a look at data, that how does it look like. Yeah, so just load it, and just it should look like this for everyone. Fine, so we are all good, I think. Okay, this is how you can get the data loaded. Okay, fine. Yeah, so let's uh, go ahead and work more on it. So here we can see we have 1, 2, 3, 4, total 4 files are there, and this data is only for the file LTC USD. Okay, so LTC is Litecoin. It is for Litecoin. Okay, I need data from all the files. Okay, I actually need data from all the files. So what should I do? I should bring in data from all the files actually. So let's have one more data frame created. I'll name it as main underscore df is equal to, and here I'll put the name of the files. So one is here, one is the BTC Bitcoin BTC hyphen USD, that is one file. Then after that, second one is LTC USD. Okay, so similar way, BCH USD, and then we have ETH USD. So all of them are there. So what I will do is I'll just get all of them loaded. Okay, so for RN RATIOS. Okay, so what I will do is here let me have pd.data data frame. This will create an empty data frame, and ratios is equal to this way. And yeah, so for all the ratios, what I will do is here print r, which ratio are we talking about, that can be printed, and data set is equal to, we will have yeah, so the whole path, already we have the whole path. Yeah, this is the whole path, Control Z. This is the whole path, and I will just remove this, and I'll have string formatting used over there. df is equal to pd.read read underscore csv, and then datact data set, and here actually I should put r, so that dynamically, and here I can put data set. Yes. Names I'll put, and names I'll put from here. So let me just display df as of now. Yeah, so let me make it ndf. So you can see that earlier it was 6 columns, still it is 6 columns, but we have 3 and we had 3 only. Okay, So earlier we had something once tens, 100,000, 10,000 lakh. 1 lakh records were there, and now we have once tens, 100,000, 10,000 lakh. Again, 1 lakh, 28,000. Okay, so other files are having little less data, I think. Okay, so most of the data is there in this particular file. Other files are having little less data, which we can see over here. But we have combined the data from all the files. That is what we have done. Now what I will do is, so this much we have done. We have loaded the data here. Okay, fine. So further formatting we can do in the second part. Okay, the second part, the second next session we can do format, and we can apply the LSTM over this particular data. So here it is clear, till this point it is clear that we are making use of this particular data where we have time, low, high, open, close, and we are planning to use close and volume, these two columns, for our further analysis. That is what we have decided. Okay, so I will add this notebook also in the classroom, and so here I'll add this notebook. Done. Okay. So I have added. So you can just refer that. Further, we'll work on this after the lunch break. Okay. So we'll have lunch. Then we will continue further with this program.